Hi, welcome to the Noise Pad. In this episode, we're going to try and see if we can fix another set of Tektronix probes. This time we have the TCP0030 current probe, some of the best current probes in the industry, very high performance, and both of these were kindly sent in by two different viewers donated to the channel so we could fix them. I'm trying to expand the probe ecosystem that I have with Tektronix because they all work with the TechVPI interface with the 4, 5, and 6 series oscilloscopes, which I have. They're fantastic instruments. I've done full reviews of those. Make sure you check them out on the channel. So here we have two different probes with two different problems, and this one has obviously already been taken apart before it was sent to me, but we'll talk about what's actually gone wrong with that one. And this one fails the degauss test, so we'll have to take a close look at both of them. I actually have a third one that I bought from eBay a short while ago. This is the TCP0020, basically a lower end model, but this one also fails it. So we're going to put this aside for now since we have two of the same one. I'm curious to see if we could make at least one working one between these two. Let me also demonstrate this first probe's failure. So we're going to plug it into this MSO4 series. There we go. And there it is. So it goes through it. It detects the probe. And you can see it's already failed the degauss. If I press it again, it does a few clicking. And it says in progress. And nope, it doesn't work. Even though it zeroes it, you can see it does go back down to 0, but it still fails. And the lights on the probe are in the correct order, but when this is yellow, basically it just means that it failed the degauss. So there is indeed a problem. So here's the disassembled head of the probe that was failing degauss. And you can see I've taken the probe transformer component out, and I have two of them because one is from the other probe, and they look almost identical. There's a minor difference in the color of the resistors, probably different years of manufacturing. But before we dig really deep into this, we need to understand at least roughly how this works, so we could swap these in and out and see what kind of combinations we can get any good result. Let's talk about the theory first. So let's consider some of the challenges we would face if we wanted to make our own current probe. Well, the very first decision to make is, do we want to cut the wire? Because as soon as you commit yourself to cutting the wire, things actually become quite a bit easier. Because you cut the wire, you put a resistor in series with it, a precision low value resistor, you put up with the burden voltage that resistor causes, and then you amplify the voltage across that resistor and then digitize it. That's basically how all multimeters do this in the most simplistic way. But as soon as you don't want to cut the wire and you're interested in measuring this unknown current, then the only thing you really can do is somehow intercept and interact with the magnetic field this wire generates. So if I could somehow measure that magnetic field or couple it into something, then that could help me figure out what the current is. That's exactly how it is done. Now, the simplest way to do that is, of course, with a transformer. We're just reinventing the transformer, essentially. We will couple the magnetic flux onto a core of some magnetic core of some kind, and the other side we will have secondary windings. And we can calculate what the output current would be depending on how many windings we put in. This works for voltage as well as current, of course. So if I were to measure the current coming out of this side, and let's say I put an AC current through this one, I would get another AC current coming out depending on the ratio of the currents. And I could measure this. And this sounds good. And this is in fact a poor man's current measurement system. This is done even in power supplies to monitor how much AC current is going through some wires. But this right away runs into several problems. First of all, if I want to measure this current at a very, very high frequency, I'm going to have to shrink the size of this transformer significantly in order to be able to support the kind of magnetic flux variation it's supposed to have. And as the frequency gets lower and lower, I'm going to reach a point where I'm going to saturate this. Or if I put too much current through it, I'm going to saturate this core, in which case then I'll get a nonlinear effect, and then you won't be able to measure the current anyway. So there are several things already in our way. And if I want to measure DC, which is even harder because the transformer, of course, doesn't work at DC. So we're going to have to find a different way to solve this problem. So in order to address all of these at the same time, they basically use the same circuitry. But then there is another additional problem in the background, that is to subtract any environmental effect. This core could become partially magnetized. How do you subtract that? Now, if you want to measure at DC, it's even more serious because depending on the magnetic field that may be around your system, that would be a complete offset, or any magnetized effect would be an offset. So you want to subtract all of that too at the same time, and you want to prevent the core from being saturated. So I think the way these tech probes do it is by adding a Hall effect sensor, which you need to measure DC anyway. Now, as soon as I add a Hall effect sensor, some really cool things happen. First of all, I can measure DC, because now any magnetic flux remaining in here can be measured with a Hall effect sensor. But then I also can wrap the Hall effect around an amplifier and have that amplifier drive the core instead. This is a feedback system, of course, and let's think about what happens here. So if I push a lot of current into this magnetic core, it becomes magnetized. Of course, it gets some flux through it, and that flux is going to induce Hall effect to produce a voltage. If I feed that voltage into an amplifier and then bring it back in the opposite direction around the coil, I can cancel that. So this closed loop system means that the amplifier is going to push enough current into this core such that the magnetic flux introduced by these turns completely cancel out the magnetic flux introduced by these turns. So there's actually nothing inside the transformer. It's in a complete closed loop system. And this also means that when you want to calibrate the probe, you can use this Hall effect sensor and magnetize this to a certain degree to completely cancel out any other external effect, or even drive it really hard in the opposite direction to demagnetize it if you have to. You can do all of these things in various AC waveforms. But this is, of course, easy to say. It's a very, very simplified diagram. These probes work up to 120 megahertz. So there's a lot of stuff that needs to happen to make all of that work. And this amplifier needs to be able to drive this. The whole thing needs to be stable over long wires. Absolutely not an easy thing to do. Quite difficult. But nonetheless, this is, I think, roughly how the architecture works. So if, of course, these transformer turns are damaged, or if this Hall effect is broken, none of this is going to work. It depends on this entire closed loop system. So now that we know this, let's take a closer look at those transformers and see if we can identify some of these components and make a measurement, especially between the working and the non-working transformer head, so we can compare them and hopefully at least find out what's wrong. Now, before I forget, I have to also mention that this technique of measuring something, bringing it back, and then canceling the signal you're introducing through a feedback system is exceptionally common. It's a powerful method of removing other unwanted effects from the system and limiting what you need to measure. This is used, in fact, in LCR meters. I've talked about this before. That RMS meter, which uses a thermal detector, does exactly the same thing. Also, it has two heaters, which balances out the amount of energy that is dissipated in there. I built a magnetic levitation experiment quite a few years ago on the channel. Uses exactly this technique where you are trying to cancel the magnetic flux in that system, in a closed loop system. So this is common. This is the benefit of feedback, of course. But you see this architecture of this kind of cancellation many times over in many devices. Okay, we have some progress, which is good. I verified that this transformer, this one, indeed works with both of the probes. So I can degauss no problem with this one, but then this particular transformer does not degauss in either of the probes. So pretty much I have narrowed down the problem to being in this head. Unfortunately, these things are like $1,200 each, just this one piece that I'm holding. But these probes are still quite pricey. So I'd like to see if there is any way to fix this. Now, I'm very skeptical. If you look at this, if this thing would focus, you can see that it's potted. Okay, so let's put it under the microscope. Let's take a look at the internal structure a little bit more and see if we could take it apart. At the minimum, I like to see how it is built, but first we also need to identify its pinouts and see which one goes to where. That would be also very helpful because we can look for differences between these two probe heads. Let's see what happens. Okay, let's see what we have here. So here's the two of them, and you can see that they're quite intricately designed, and all the wires inside are clearly handmade. Look at all the thin wires going into these interfaces. They're, I think, identical as far as I can tell. The resistors, the big resistor there that I think is part of the transformer, is also identical. Is all potted, of course. So it's somewhat soft. Yeah, it's soft. So we might be able to do something about that. Same with this one. And the broken one is this one. That's the one that doesn't work. Now all these cables must be the Hall effect sensors as well as the primary transformer. I see a few different colors in there. So we have to do some measurements. It looks like they all go to the side here. Let me remove one of them so we can take a closer look. So in here you can see the interface. So they all go into these pins, and these pins then go into this connector. So we should be able to track that. Now if one of these cables is bad, I would be really surprised because this thing cannot move anyway because it's all potted down. But nonetheless, we should be able to make some comparative measurements. So here's the two transformer heads that you can see, and there's a other opposite part of it. So this is the top of the probe head. You can see this doesn't have any electronics in it, but these two mate on top of each other like so. And when they're closed, you basically have a complete transformer like that. That's pretty neat, and that's the biggest wire we can put through this. There's a piece of plastic that's supposed to go in here. That piece of plastic is broken for both of these probes, so we're going to have to think about something to fix that anyway. Maybe a very thin piece of Teflon will fix that, but let's get to that problem later. Right now we see if we can fix this one. All right, let's do some investigation. So some more discoveries here. So this is what's inside of the probe head itself. There is an inline transformer in here. We have two coils that are coupled together through the ferrite core in there, and I think this could be for things like common mode suppression or some stability control. It's hard to know without looking at the details of the circuit, but that's interesting that they need that. Now if I flip this to the other side, in order to get some estimate of what the pinouts look like, you can see that we have two thicker traces here. I believe these are going to the transformer inside of the transformer head, and then we have four other pins, two of these with two thin lines coming out of them, and if I flip it to the other side, the other two, we have another two thin lines you can see coming over there, end up over here. So all of these must be to power the Hall effect sensor, as well as have the data from the Hall effect sensor go back into the probe head itself. So all these signals need to go back and forth, and then when this thing is actually assembled, is assembled like this. So you just basically plug them in like that. So using that, we should be able to do some relative measurements between these two transformer heads and make sure all the components are actually there. And from there, hopefully, we can draw some conclusions. Okay, let's see what we have here. So here's the wires of the working transformer, primary or secondary, whichever one you want to call it. And we have 1.4 ohms. So that looks good. And I can take this exactly and plug it into the one that doesn't work. And we should be getting something similar. Look at that, 1.4. Okay, so that means that the transformer windings are actually working. So that's a good sign. So the next thing we need to check is that if the resistances of the Hall effect sensor are the same. So here's two of the terminals of the Hall effect sensor on the working transformer, and I think this is the power ports. So we're seeing about 272 ohms, which is, I think, normal. I don't know what kind of Hall effect sensor they're using, but that doesn't seem like an unusual value. Now we can switch it over to the non-working one. Let's put it down, and we get nothing. Okay, so right off the bat, there is definitely a problem. It looks like there's a disconnection, or maybe the Hall effect sensor is dead, but it's likely that it is disconnected because the resistance is in the tens of mega ohms or higher. We can't even measure it. So it looks like the pin that is not connected to anything is this one. And it does have a tiny trace, and it goes into that tiny little pin over there, and from that on the inside, we have a wire connected to it. I'm just going to do a very quick touch on this with a soldering iron just to make sure that the wire is just not disconnected immediately after that. Well, reflowing it did not help, as I was anticipating it not to do anything anyway, but now we're in desperate measures. So we're going to have to really take this apart. It may be fully destructive, but it doesn't matter. For the content, we're going to find out exactly what it looks like on the inside and see if it's really just a disconnection of the Hall effect sensor is entirely dead. Well, as expected, this thing was not designed to be taken apart, and it is a destructive disassembly, but there's a lot here we can now learn about. Yeah, you can see that these wires are all messed up. That's probably what I did while I was trying to separate it. So this actually sits inside of two, not just one, but two of these cavities inside of each other, very carefully designed with various insulators in the middle. This is, I suspect, all to contain all the magnetic flux, because this thing is active. So if you radiate out of it, it's going to be a disaster. So a lot of work has been obviously done to preserve that. So I think we should at least take it apart a little bit more and see if we can find out what is happening. Interestingly enough, there's actually another transformer in here inside of this resin material, and these are all the cables that were coming in. One of these is the one that is broken, and I can't know if this is what I did or if it was broken from before. It's really hard to know. But let me do some more destructive disassembly here so we can see it more. So the Hall effect sensor is really nicely incorporated into the transformer body without disrupting its magnetic field significantly. You can see the contacts on the right side. There's two wires, one here and one here. And then this thing just sandwiches together like so. And that's your entire two sides of your transformer. If I can hold it in one place. There it is, like that. That's really great, and I can see why this thing costs so much money now. There's so much manual labor in this. It's all hand assembled, and this is the other side of the transformer, so you close it up like that. They meet like this. It's really nice, and yeah, well, there's no way to repair this really after seeing what goes inside of this. That's really cool. There's another inductor in there. Yeah, there was no way, but nonetheless, we got to see how it is made. More importantly, we got to see this really cool Hall effect sensor assembly. That is really neat. I don't think I've ever seen that this close, like that. Very cool. Well, we have one more probe there, so at least let's close that back up and make sure it works correctly. Well, disaster has struck. I closed this back up and it was failing degauss again. Took it back out, measured the resistance on the same two ports, and guess what? It's now open. I don't know what happened. I literally just put it back together. It must have been really close to failure. Now, sometimes if I squeeze it really hard this way or squeeze it really hard that way, I can temporarily make that connection come back, which is consistent with what we just saw in the teardown. We had these two plates and those connections that can very easily separate. Basically, if you have one of these, you should absolutely never put any pressure that forces these things apart in any way, because you will break that connection in the middle. They're maybe quite sensitive, and it's a very common failure of these things. This also means that if you find these on eBay and they basically say that the degauss function doesn't work, it's most likely in this. And I was mistaken. These things are almost $2,000 each. So they are really expensive. And well, if you buy a probe body, let's say, and then you pay a couple of $100s for that, and then you buy one of these from Tech and repair it, well, that's still economical because the probe is more expensive. But if you still end up paying a couple of thousand for these, and then you still have to fix that, it's just not worth it. And there you have it. I hope you enjoyed this. Despite the fact that we couldn't fix it, we still learned something about the failure mechanism of these transformer built in, how they are manufactured, which is quite cool, and also learned about how the probes actually operate. As always, let me know what you think in the comment section. As always, I'll see you next time.